Hey there, Adrian Rosebrock here from PyImageSearch.com, and today we're going to have an introduction to hyperparameter tuning using Python and the scikit-learn library. Throughout the series of tutorials, you're going to learn about hyperparameter tuning. We're going to start with just the fundamentals of it. Then we're going to move on to tuning hyperparameters in a computer vision project. And eventually, you're going to learn how to tune the hyperparameters to deep neural networks. You're going to learn how to do that using scikit-learn, and you're also going to learn how to do that using some deep learning models and some deep learning libraries, which will be really, really cool. Because I get asked, all the time, how do you tune the hyperparameters to your deep neural networks? How do you know how many filters to apply to a convolutional layer? How do you know or what the proper learning rate is or what the batch size is? And some of those parameters are easy to intuit. Once you've run hundreds or thousands of experiments, you develop this sixth sense of what works and what doesn't. But until then, it's good to learn how to tune these hyperparameters because you're literally leaving accuracy on the table. I like to explain hyperparameter tuning in terms of like old time radios that either you own or your parents own or your grandparents own. But with these old time radios with AM and FM, these non-digital radios, you actually had to manually tune what station you wanted to tune into, and then you might have to change some equalizer settings. It was a lot more work than just simply logging onto a website and just pressing play, to get your audio content. It was a lot more work. And what you would notice is that if you were tuning the AM or FM dial, sometimes you'd be able to like land right in between the frequency of two stations, and you get this cacophonous noise coming into your ears. You get bleed in from one station and bleed in from another station. And what that indicated was that, well, you got to tune that dial a little bit. You got to get onto that signal. You got to lock onto it so you can hear what it is that you want to hear without all that additional noise. So, in terms of hyperparameter tuning, think of all the knobs and dials of a machine learning model. I'm not even talking about neural networks, which have an incredible number of parameters. I'm just talking about your basic logistic regression model or your support vector machine. Those have parameters that you need to tune. And if all you do is just import an implementation of one of those models into your library, well, you could be leaving accuracy on the table. A few weeks ago, I was hanging out with a good buddy of mine, and he's an expert poker player. And him and I were kind of talking about the differences between being a smart poker player and tuning parameters to a machine learning model. And I came up with this example, and I said, okay, so you're sitting at the table and you're playing Texas Hold'em. So you have your two cards in front of you, and one of them is a king. And then on the flop, the first three cards dealt to the table, you see three kings, and you're holding the fourth, right? So you know you have four of a kind, and there's a very high probability you're going to win that hand. So the question becomes, how do you maximize the return on your hand such that you win the most money from it? For your more aggressive players, you may choose to go all in really quick. You want to own the table. You want to establish the dominance of the table. And the aggressive players may think, man, he's just bluffing. There's no way he has that other king. And you may be able to get them to come in quickly and go at you quickly because they think you're bluffing. Now, on the other hand, if you're playing with a bunch of passive players, they're going to be a little more slow to play. They want to be cautious. So maybe you just progressively bet them up a little bit. You work the table a little bit. You kind of sucker them in until you win the hand. Because otherwise, if you don't do that, if you don't play the table correctly, then people are just going to fold, and you're not going to win that much money from this amazing hand you've been dealt. Machine learning and hyperparameter tuning isn't all that different. You've gone through all the effort of writing this complex code, of learning a new skill, you're importing your model, you're loading your data set, you're pre-processing it, and now you're ready to train it. And if all you do is train it using the default parameters, there's a chance that you could be leaving accuracy on the table. And in some cases, that accuracy gain may only be 1% to 2%, which can be significant depending on your application. Or on the extreme end, you could be looking at 25, 30, 40% gains in accuracy just by tuning your parameters. And I'll specifically say if you're using support vector machines with nonlinear kernels, you have to tune the hyperparameters to those models. SVMs with nonlinear kernels can be a real pain to tune, and if you don't get them just right, your accuracy is going to suffer. So what we're going to do today is just look at how to tune the hyperparameters to a support vector machine specifically applied to regression. We'll be using the abalone dataset here, which is from the UCI machine learning repository. And if you're not familiar with abalone, they're basically just water snail-like creatures. And scientists have been studying them for years, and one aspect that interests them is predicting the age of these abalone. Now, typically, you would do that kind of like measuring the rings in a tree. You would count the number of rings in a tree after you cut it down to learn how old that tree is. With an abalone, you do this something similar, but with these creases in the shells. Now, obviously, that is a very tedious, time-consuming task. So researchers were wondering, hey, is it possible just by taking measurements based off of these shells, like the length, the diameter, the height, maybe like the weight of it, the sex of the snail, is it possible to automatically compute the age and therefore, or the number of rings and therefore the age of the abalone? Is that possible? It turns out, yes, it absolutely is. And what we're going to do today is learn how to use this data set and train a model on it, tune the hyperparameters, increase the accuracy of our system. So let's look at our project directory structure here. This CSV file here is our abalone dataset, and if I open it up in PyCharm, well, let's look at the config first because we have here are the columns of what's in this CSV file: the length of the shell, the diameter, the height, the whole weight of it, the weight of the shucked weight of it, and then the weight of the viscera, or the meat, the shell weight itself, and then of course this is the age. This is the value we want to predict. So these values here, this is our feature vector. This is the data that's given to us, and our goal is to take this data and be able to predict the age of the particular water snail. So if I open up this CSV file, here is the data. Here are the features: the length, the height, the width of the shell, the weight, and then this is the age, the last column here. So we're going to use this set of data to predict this particular value. So that's what this CSV file is. Inside the PyImageSearch module, we have a configuration file, and then we have 3 Python scripts. The first one here, train svr.py, that is going to do no hyperparameter tuning whatsoever. We're just going to do an import. We're going to load the data set. We're going to train the model and see how performance is. Then we're going to run a grid search, which is a type of hyperparameter tuning algorithm, as well as a random search. So what's the difference between them? Here is a great example image that I like to use to explain the difference. So with a grid search, let's say we have 2 hyperparameters with 3 distinct values that they can take on. So we'll plot the hyperparameters, the first hyperparameter along the x-axis and the second one along the y-axis. A common misconception with hyperparameter tuning is that some machine learning practitioners, especially those new to machine learning, think that in order to obtain optimal model performance, there is only just one unique set in the entire universe of possible values that these hyperparameters can take on that will obtain optimal performance. So once you find that particular value, you're good to go. There is no further searching required, but you have to spend a tremendous amount of time trying to find that singular set of optimal values. That's actually not the case. How it actually works is there's a distribution. There's a range of values that these hyperparameters can take on. And as long as you land within that range, you're okay. You don't need to find this one optimal set because that's not really how hyperparameter tuning works. There's this distribution, and you just got to land somewhere in that distribution. And as long as you do, you'll find the optimal hyperparameters for the problem. So a grid search is an exhaustive search. First, it's going to say, I'm going to select a value of A for hyperparameter 1, and a value of Z for hyperparameter 2, and I'm going to evaluate it. And I'm going to go on to the next one, again, keeping a value of Z for hyperparameter 2, but this time I'm going to use a value of B for hyperparameter 1. And it will do every single one of these evaluations. That is a very, very exhaustive process. And the worst part is that this is only 2 hyperparameters. What happens if you have 3 or 4 or 5 or 10 that you want to test? With a grid search, you're creating these exponential combinations of parameters. So for each parameter you add, and with each value you add, you're exploding the number of possible combinations. That means that it's going to take a long, long time to run a grid search just by nature of how this algorithm works. On the other hand, you could use something called a random search. So you're going to do the same thing. You're going to define these hyperparameter values, but instead of having singular values like this, what you could also do is define them in a range from the starting point to the midpoint, and then you're going to run a number of trials, say 10 trials. So for each trial, you're going to randomly sample some of these hyperparameter values, train the model on it, and evaluate it. The benefit of that is that you're going to be able to cover a larger distribution of values in a shorter amount of time. And again, this white area here, this is the optimal hyperparameter value. This, as long as we get something in this range, will be good. With a grid search, you're not necessarily guaranteed to land in that range because maybe the hyperparameters are not spaced correctly. With a random search, you have a just by definition of how the distribution works, you're going to be selecting values between an upper and lower range. So it's going to cover more area, which is an interesting, which is almost counterintuitive, right? Because grid search, you're running more trials, you're running more trials. Shouldn't that cover more area? Well, no, not necessarily, because there's going to be spaces in between those values. And with a random search, it actually makes it a little bit more likely that you're going to land in that optimal hyperparameter zone, especially as you increase the number of trials that you're running. So we're going to implement both grid search and random search here. So let's dive into the code. Let's take a look at our config file first. This is a simple config file. We have the CSV path to our Abalone training CSV file, which resides on disk. And we've already reviewed the columns of the CSV file. They map to the values in each of the columns here. So let's look at training a standard support vector machine regression model with 0 hyperparameter tuning. We have our imports here. We have our standard scalar. So we're going to load this data set from disk. And then we're going to do a column-wise scaling, which is a standard score or z-score in the statistics world. So what you do is for each column, you're going to compute the mean value here, and you're also going to compute the standard deviation. So for each value here, you're going to normalize it or scale it by taking the particular instance, subtracting the mean, and dividing by the standard deviation. This is a standard score or a z-score, depending on what statistic book you've read. And it's a pretty common scaling method used when working with this type of data. So that's what that is doing. We have our training and testing split function, our implementation of the support vector regression model, and then pandas is a data science library. It just makes it super, super easy for us to load the CSV file and work with it. So with that said, let's load the CSV file from disk, and then we're going to grab our feature vectors here. That's data X, and that's everything but the final column. So this is like your shell width, your shell height, the weight, and then this value here, this is the age. This is the value you want to predict. So again, this is the features, this is the age, the value that you want to predict. And we're going to take all that and construct a training and testing split using 85% for training and 15% for evaluation. Here's where our standard scalar comes into play. So we'll create an instance of it, then we'll fit and transform the training data. So what we do here, the fit here, this is where we're computing the mean and the standard deviation. So we're examining the column-wise data of specifically our training set. And then once we've computed the mean and standard deviation, the transform component actually performs this calculation, x minus the mean divided by the standard deviation. The test x data, on the other hand, we just need to call the transform component. Well, why is that? It's because we're separating our training and testing set. We want to keep our testing set separate from the training data so we can get an unbiased opinion or unbiased empirical evidence on how our method is performing. So you never call the transform method on the testing set. You fit it first on your training set, and then you transform it on the testing data. So now we're going to initialize our support vector regression model with the default hyperparameters. No hyperparameter tuning required whatsoever. Let's just see what our model does. Then we fit it on the training data, and then we evaluate our model using the R-squared score, which is going to tell us how well the correlation is between the input data and how good of a job we are doing at making predictions. So we're going to see, is our model correlating well, predicting the age correctly? Where 0 is not correlated at all and you're doing a very poor job, and 1.0 is correlated 100% accuracy. So when we run this model, I'll show you the output here. We get this score of 0.55, which means there's a decent correlation between the data we have here and then the output predictions. And notice the runtime. We have 1.3 seconds to train this model. The question is, can we boost this accuracy further by doing a hyperparameter search and tuning the parameters to the support vector regression machine. Let's take a look at that by looking at the grid search. Again, we start off with our config. We have this repeated k-fold validation. When you're doing a hyperparameter search, you typically want to do this concept of k-fold validation. So you take your data, your training data or your testing data, and you split it into k equally sized pieces. And then you train the model on n-1 of these folds and then evaluate on the other fold. And then you repeat the process for each combination of the two. It does a really good job of evaluating the model amongst different splits to give you a good idea of how well your model is performing. Our grid search CV method here, this is our implementation of the grid search algorithm that I was telling you about over here. Standard scaler again, support vector regression machine implementation, train test split, and then our pandas CSV file parser. So again, this code right here is identical to the previous examples. We load the CSV file from disk, grab our feature vectors, and we grab the target age of the abalone we want to predict. Training and testing split is constructed here. We do our scaling, and then here's where things get interesting. Here we initialize our support vector regression machine model, and we also want to tune 3 parameters here. We have our kernel, the tolerance, and C. C is like the strictness of the support vector machine. This controls the degree in which the support vector machine is allowed to make mistakes. The larger the C value, the more hard classifier you're creating and telling the support vector machine, absolutely no mistakes. Don't make a mistake on this training data. The problem you get there is you may create overfitting by having too large of a C value. On the other end of the spectrum, though, if your C value is too low, and you're going to create this soft classifier. It's allowed to make mistakes. So you may introduce too many inaccurate predictions. So it's a balance you need to strike. And furthermore, the kernel is really the most important part of the support vector machine. That's when you do the kernel trick and project your data into higher dimensions. Your hope is in that higher dimension using one of these kernels that your data is linearly separable. But in order to get that to work, you need to specify the correct kernel and the parameters associated with it. So we define these parameter values and then create this dictionary, this grid of parameters that we're going to search over. So when performing a grid search, we're going to examine every single combination of these hyperparameters. So here we create our k-fold cross-validation. We're going to use 10 splits, repeat this process 3 times. And then we start the grid search here. We pass in our estimator, which is the support vector regression machine model, the parameter grid. These are the hyperparameters that we're going to search over, just like this. Here is the hyperparameters of the grid search, but instead of having 2 hyperparameters with only 3 values, we have the kernel, tolerance, and C. We have 3 hyperparameters, each with multiple values associated with them. So we pass in the grid, and then number of jobs we set to -1. What is this jobs value control? That's the number of processes or cores that scikit-learn is going to utilize on your machine when performing this grid search. So a grid search can be ran in parallel provided your machine has enough memory to run multiple instances of this training job. So in order to speed things up, we can specify the number of processes or the number of cores on our processor when running a grid search. Using a value of -1 tells scikit-learn that you want to use every single processor, every single core on your machine. So that's what this value is doing right here. It's saying distribute this search process over all cores across all processors. Here is our cross-validation fold for evaluation. And then we want the scoring method we want to minimize here is mean squared error. So we want the smaller the mean squared error, the better we are at making predictions of the age of the abalone. So once that's done, once the grid search is constructed, we'll run a fit on it, passing in our training data. And this is going to exhaustively try every single combination of these hyperparameters. And once that's done, we'll grab the best model from the search and evaluate it on our training or on our testing set. So if I were to run this on my machine, you would see that this script would take 4.5 minutes to run versus 1 minute of just doing normal training. The benefit, though, is we boosted our R-square value just a little bit. So that implies that we did improve our accuracy by running this exhaustive grid search. But is it really worth the 4.5 minutes of runtime? That's a lot longer. is there a way that we could reduce the search time and still maintain that accuracy without having to do this exhaustive search? The answer is yes. We use a random hyperparameter search. So let's take a look at that implementation. We start off with our config as the import. Again, use our randomized search, or excuse me, we'll again use our repeated k-fold search, but this time we're going to use this randomized cross-validation search for tuning our hyperparameters, which essentially allows us to sample hyperparameter values across the distribution, and ideally will land in the ideal zone for these hyperparameter values. Again, standard scaling is used for processing. Here's our support vector machine regression model, training and testing split, and then we use the log uniform here function to generate the distribution of our tolerance values, and then pandas for our data science utilities, specifically loading the CSV file from disk. So this code here, this is all the same from our previous example. Load the CSV file from disk, grab the features, grab the age of the abalone, construct our training and testing split, and then scale the data using standard scoring or z-scoring. Here we define the hyperparameter search space, so our kernel, our tolerance, and our c-value. And then we'll construct a dictionary based on that. So here's where the randomized search comes into play. We'll construct our repeated k-fold set of data, 10 splits, and we'll do that 3 total times. And then here we initialize our randomized search. We pass in the model, which is the support vector machine that we want to optimize. We specify a negative value for the number of jobs, implying to use all cores of our processor. Here is our cross-validation folds, our parameter distribution grid, which is this right over here. And then our scoring method, again, we want to minimize the mean squared error. We call randomsearch.fit with our training data. This will do this randomized search across the distribution of our hyperparameters that we defined here. And once the hyperparameter search is complete, we'll grab the best model and evaluate it on our training and testing set. So to show you the output of this, you'll see the output of running our randomized search here. And notice our r-squared value is at 0.56, exactly what it was when running a grid search. But look at the timing. It only took 36 seconds to run this search compared to the 4 minutes and 34 seconds with the grid search, yet we obtained identical accuracy. This is fairly common. This is something you'll see when applying a randomized search, and that's as long as the number of trials is high enough on the random search, you'll typically be able to get the same hyperparameter accuracy as if you used a grid search, but you'll be able to do it in a fraction of the time. And it also is just a bit nicer to code with a randomized search. You just define the parameters that you want to search over, and a random search just samples here and there from them. A grid search, on the other hand, is exhaustive. It tries every single combination of the parameters, very time consuming, takes a long time to run, and you're not guaranteed better accuracy than if you just used a random search in the first place. So I recommend trying to use a random search whenever you can. I'll show you how to use a grid search though for a computer vision problem in the next tutorial in this series. And from there, we'll move on to using scikit-learn and some deep learning specific models to tune hyperparameters to deep neural networks. But for now, understand the importance of hyperparameter tuning. And that's simply if you're not tuning the parameters to your model, you're leaving accuracy on the table. It is well worth running some of these experiments to get an idea of what parameters work well when. And when you do that, you develop this sixth sense. And over time, after running hundreds or thousands of experiments, you'll literally be able to look at problems and, without even thinking about it, come up with initial good hyperparameter values. They may not be optimal, they may not be the best, but you're going to be far, far better at selecting these initial values than you were as a novice machine learning practitioner. Because let's face it, machine learning, especially tuning hyperparameters, is part art, part science. It takes time to develop that skill. So start early, practice now, and that skill will come to you far, far easier. I'll see you in the next tutorial in this series.